All right, let's look at a couple of more things before we close out this chapter section. This chapter section is entitled The Remainder and the Factor Theorem. And interestingly enough, we're going to look at the remainder theorem and the factor theorem and how we can use synthetic division or how those theorems support synthetic division. So the remainder theorem, now what it's saying is if I've got a polynomial function, a function that's got polynomial equation, and I am given a value for x. In this case, we're deriving that, where c is equal to 3. This starts out with the x minus c. And if we substitute in the 3, we got x minus 3 equals 0. X is equal to 3. That if we divide that by the 3, and if we get a remainder from that synthetic division, that remainder is in fact the same as or equivalent to the value of f of 3. So in other words, if I substituted in a 3 for each of these x's in this polynomial equation, and I calculated it, that calculation would equal the remainder value of dividing that polynomial by 3. So let's do our division. So we got 3 in the box. We'll drop down our 4. We'll put our coefficients in. 4 minus 3, 1 minus 6, 8 minus 15. Drop down the 4. So 3 times 4 is 12. Minus 3 plus 12 is 9. 9 times 3 is 27. 1 plus 27 is 28. 3 times 28 is 84. Minus 6 plus 84 is 78. 3 times 78 is 234. 8 plus 234 is 242. And 3 times 242 is 726. And minus 15 plus 726 is 711. So then we could write here that f of 3, given this polynomial function, is equal to 711. Now, it seems much easier to do this by synthetic division to come up with this value of f of 3 than it is to plug in everything into this polynomial. However, I could graph the polynomial, y equals, put it all in, hit graph, then hit table, go in and look to see what x is. And if I did graph this, put this in my graphing calculator and graph this, and went into the table, I would discover that when x is 3, y is 711. There's an example of the remainder theorem at work. All right, well now let's talk about the factor theorem. And so what the factor theorem states is, if I divide a polynomial by an expression, x minus c or x plus c, and when I do that, if my remainder is 0, then that expression is in fact a factor of the polynomial. And if my remainder is something other than 0, then that expression is not a factor of the polynomial. So here we go. We've got a function equation, x to the 4th minus 2x cubed minus 9x squared plus x plus 6, and I'm given 2 expressions to divide that by to determine if either of these is a factor. So let's start with the x plus 2. And of course, on the setup, x plus 2, set that equal to 0. So I'm going to divide by x minus 2, synthetically divide by x minus 2. So I put minus 2 in the box. And minus 2 times 1 is minus 2. Minus 2 times minus 2 is minus 4. Minus 2 times minus 4 is 8. Minus 2 times minus 4 is 8. Minus 9 plus 8 is negative 1. Minus 2 times negative 1 is 2. 1 plus 2 is 3. Minus 2 times 3 is negative 6. And 6 minus 6 is 0. So x plus 2, yes, it is a factor because we have a 0 remainder. Now I can take what my quotient is from this, since it is a factor, and drop it down, and now synthetically divide by the x minus 1, and of course x minus 1 is I'm going to synthetically divide by 1. So I've dropped down my coefficients from my previous, where I solved previously. So now I've got a 1, a minus 4, a minus 1, and a 3. Because if it's a factor, it's going to be a factor of this equation here. And this equation here would really be x cubed minus 4x squared minus x plus 3. All right, so I bring my 1 down, got my 1 in the box. 1 times 1 is 1, minus 4 plus 1 is minus 3, minus 1 times minus 3 is again minus 3, minus 1 minus 3 is minus 4, 1 times minus 4 is minus 4, and 3 minus 4 gives me a remainder of minus 1. So x minus 1 is not a factor according to the factor theorem. Therefore, the factors of x to the fourth minus 2x cubed minus 9x squared plus x plus 6 are x cubed minus 4x squared minus x plus 3 and x plus 2. Those are the factors of this polynomial according to the factor theorem.